matrix. And so for the first operation is we rotate about the 3 axes by the angle omega. So that is the step 1. So for this case, we can have, in terms of the notations, the new coordinates is in terms of epsilon eta zeta. So the old xyz, and that is in our IJK coordinate system. And from here, corresponding x-axis moving to zeta. So here, let me put the zeta prime and eta prime, and then notation zeta prime here. Okay, so here about the 3 axes. So let me quickly put the simple one here. Okay, so again, using this one, you can project this axis into the 2 axes, and look at that carefully. Let me plot this one more time. So basically, this is I-axis, J-axis, and right now this is our epsilon prime. Okay, and this one rotates by angle omega. So from here you can see basically we project into 2 components. This one is cosine, so cosine omega, and in I direction, so corresponding to x. And this amount is sine, and in z direction, so that is sine omega. Okay, in the similar way, and we have another axis, and that is eta prime. Okay, so you can do the same thing. So quickly, this is sine omega, cosine omega. Okay. So this one is we defined as the R1. Okay, so the next sequence, starting from zeta, eta, and zeta prime. Okay. So here, whatever the coordinate systems, let me skip this kind of this thing. It's not critical here. So now for the second coordinate system is we rotate about this axis. So this axis is, let me say that is the first axis, okay? So the first axis, and by the angle I, because this is the axis is basically is moving from this one. That is I will define the one axis. Okay, so let me use that symbols. So for these operations and to the symbols we're going to pick up is. Let me look in here. So basically, the new coordinates transformed from here is defined as this one. Okay, there's a no prime. So here, no prime here. Okay. So now again, here we rotate about the second operation is about this axis. So here the 1, 0, 0 should be here. This one is equal to the original axis and 0, 0. Okay, and now again we can have this one expressed. So let me put into here in the original axis. This is zeta, and this is the zeta here. Okay, once we transform, this is our new axis here. Okay, so this axis right now expressed in these 2. And this one, basically, we rotate is by angle I. So in a similar way, you can project, and from here to help you, write down the components. So basically here, this is cosine. Amount is cosine I in prime direction. So cosine I in prime direction. And this is a sine I in zeta prime direction. Okay, in a similar way, the other one is zeta, so this one is I. So quickly you can do the same thing. So that is sine and cosine. Okay, so this one is defined as our second rotation matrix RQ. And now we come to the third one. The third one is we rotate this axis. And this one is converted from here. It's transformed from here. So this is in terms of a number. Let me call this called the axis 3. So we rotate the axis 3 by omega, small omega. So here is the notations. Okay. So for this case, we align the thumb rule and align our thumb rotating in that directions. So under that situation, from the old corner systems, theta and eta, theta, okay, to, again, per our notations, this one will be moved to x, and this will be x, and z will be the same thing, this will be y. So again, zeta is corresponding transformed to x-axis, and zeta, this is y-axis. This one remains as our local z-axis, and this one is our PQW corner systems. Okay. So again, per our notations here, so we have the similar way, and right now we're rotating about 3 axes, so that is 0, 0, 1, 0, 0, 1 here. Okay. And in terms of the notations, again, let me try to draw this one. So right now, this axis want to express in terms of epsilon and zeta. Let me draw this one. So this is epsilon, and this is the zeta. So this is our x-axis. Okay, that is from, if you look at this graph carefully, okay, right now this one is, due to this rotation, this axis is moving from here. So here this is our angle omega, so the same thing, projections. So this amount is cosine omega in that direction. So cosine omega should be corresponding to this one. And this amount is sine omega in this direction. So sine omega corresponding to this one. Okay? And this is our y. So in a similar way, that should be minus omega and sine omega. Okay, so this one we define is our R3. So therefore, again, we can write it up, the transformation, the formula. So basically here, xyz will be equal to R3 multiplied with the 3. Okay, the 3 in terms will be equal to R2 multiplied with this one. And the 3 will be in terms of R1 multiplied with xyz. So here is 1. So here is our PQW in xyz, and in PQW, and then here is xyz in our IJK corner systems. So that is the transformation matrix. And again, here is all the symbols, and we can derive, but you don't have to, because once you have the individual, the orbital elements, you simply using MATLAB or whatever software, you just do the calculation. Okay, and textbook provides us the expanded formula, and that appears, I think, on one side of your handout. So, and that one basically for your reference. But it's not necessary. I think one hand counts. I can double print it. Yes. Okay, you don't need to expand, but that one kind of expanded expression for this provided in our textbook. Okay, I don't think that function, that formula is very useful. I don't think so, and very easily you can make mistake when you plug in. So my recommendation is you simply calculate individual R1, R2, R3, and then do the multiplication like this. Then that'll be easier. Okay. So that is for the transformation between the systems here. And so right now we've pretty much finished all the transformation of the matrix, and the next one we're going to go back to our topics and talk about the more the practical application of the transformation matrix. So next one.